Hello everybody. This is the examples video, but I want to caution that when I'm showing examples, I'm not showing you steps for how to get answers, because that's not the big picture that I want you to get. Here's the big picture that I want you to take away from these examples. You see three rational functions here. And a rational function is just a polynomial divided by another polynomial. And they look pretty similar to each other. Like here I've got 10x plus 5, here I've got x plus 5, here I've got x plus 10. So like a couple of changes in the numerator. The denominators are also mostly the same. Here I've got a plus 50, here I've got a minus 50. But if you look at the graphs, this graph looks like that. It's all one piece, maybe a horizontal asymptote, hard to tell. This graph seems to have two pieces. It looks like a transformation of 1 over x. Is it? I don't know. And then this one seems to have like three pieces. It's got vertical asymptotes. Where are they? So here's the big picture. The questions I want you to be able to answer is I want to be able to give you any rational function, and you should be able to look at it and understand and predict what's it going to look like. But more importantly, say, why is it going to look that way? And it's not about graphing. Like if we wanted to graph, we would just throw them into Desmos the way that I'm doing. The purpose of being able to predict what it's going to look like is understanding the algebraic structures that produce certain types of behavior in the function. Because that understanding of like what equations are doing is going to get extended in further math courses, whereas you're not going to get asked to graph more and more complicated things. So it's not really about the graphing. So that's the first thing. If you see an equation, what do you think it looks like and why? And then the other question, which is related, is what range of things is possible? If you have a polynomial divided by a polynomial, what are all of the different ways that could possibly look? And even more, if you have a goal in mind, could you invent a set of equations? Could you construct a rational function that looks the way you want it to look? So the short answer to what makes these look different is it has to do with two things. It has to do with the factorization of the numerator and the denominator. Because if you rewrite each of these polynomials in factored form, the factors are like the building blocks that are used to build the polynomial. So understanding what the factors are is going to have an influence. And then the second thing is what's the degree of each polynomial? How does the degree of the numerator relate to the degree of the denominator? So let's start by factoring. So on the left-hand side here, the denominator doesn't factor over the reals, so you can't factor that anymore. On the right-hand side, you'd factor out a 2, and then it's a difference of squares, and so you get the same thing here. So why does that make a difference? So let's start with this middle one. You might notice that x plus 5 divides x plus 5 to be 1, but what does that mean for the graph? What does that mean for the behavior of the function? I could just reorganize this a little bit by pulling out the two x plus 5s, and it looks like this. And what you'll notice is this term is really the same as 1. So what you'd expect to see is you'd expect this graph to look exactly like that graph, because really this graph is just this function is really just the same as that function multiplied by 1, with one note. It's not strictly true to say that this equals 1. This equals 1 for all x values except x equals negative 5. Because if you plug in negative 5 here, it produces 0 over 0, which is undefined. So the original function is undefined for x equals negative 5. If you simplify it, this new function is defined for x equals negative 5. So what does that mean? That means that this simplified function looks exactly the same as the original, except that it doesn't have a hole. So whenever you have two terms that divide to be 1, what happens there is you have a hole exactly at the locations where that piece would be undefined. What else do we know about this? So we know that if we plug in x equals 5, we're going to get some non-zero value divided by 0, which is characteristic of a vertical asymptote. So if I was going to predict what was going to happen here, I'd predict vertical asymptote at 5, and I'd predict a hole at -5, which came from this fancy 1 up here. Okay, what about end behavior? So remember, the end behavior refers to what's happening as x approaches infinity or x approaches negative infinity. So you can look at dominating terms. So if there's only one term in the numerator here, which is x. So I'm going to say this is approximately equal to x divided by, and then in the denominator, 2x is the dominating term. So my original function simplifies. And then if I only imagine extremely large values of x, it's approximately equal to the two dominating terms, which means that it's not exactly the y value you'd get if you plugged in x here, but it's very, very close to the y value. And that's what it means to be an asymptote. It means that the y values are getting closer and closer and closer to something. So if you look at this simplifies to 1/2. So that tells me that there is, in fact, a horizontal asymptote at 1/2. And then if you were just going to plug in a couple of points, you could fill in the middle bits to figure out that it has to look like this, except remember that there is a hole at, -5. So that was invisible in the Desmos graph. The Desmos graph doesn't show you holes. But what I want you to do now is go back to your mindset in the original equation. Like you saw this equation. How could you have predicted it looks like this? What you do is look at the factors in the numerator and the denominator. Any factors that divide to be 1 produce holes. Any factors in the denominator that are going to give you an undefined value are going to produce vertical asymptotes. And then the horizontal asymptote comes from thinking about the end behavior when x gets very large. And you can think about, and one of the tools to think about that is thinking about dominating terms. So let's apply that same kind of thinking to this one right here. So here you see that the factors in the numerator don't divide anything in the denominator, or rather the denominator doesn't divide the numerator. So nothing simplifies. So what that tells us is that there aren't any holes. I see two vertical asymptotes here. So if I was going to sketch this, I've got one at -5 and one at +5. Let's think about end behavior. If I multiply all of this out, the dominating term, if I multiply all of this out, it's approximately equal to the two dominating terms, which would just be x squared in the numerator. And if I were to multiply all of this out, I'd have a 2x squared term here. And so the horizontal asymptote here is exactly the same. It's 1/2. And then again, you could sort of plug in values to figure out where the middle bits are. So let's just do that real quick. If I plug in 0, what do I get in the numerator? I get, I don't even need to know what number it is. I just need to know, is it above or below 1/2? Because that forces the curve to either be this way or that way. So if I plug in 0 in the numerator, so at x equals 0, the numerator is going to be 10. The denominator is going to be 2 times 5 times -5. So overall, this is a negative number. And so that means that I know it's got to look like this, because I know all of the values are going to be below the asymptote when x equals 0 in that region. So these other ones are going to look like this, and you can verify that by plugging in a value that's larger than 5 and smaller than -5. All right, so what about this one? In this one, as I said, the denominator doesn't factor over the reals. So that means not only does nothing cancel here, but there also are no x values that would make the denominator 0. So that also means no vertical asymptotes. So that's why, but let's think about end behavior. If I was going to make x very large, this function is approximately equal to, let's see, it would be 10x divided by 2x squared. And if I simplify that, that gives me, what, 10 over 2x. So what does it mean to say, because over here I got a number, right? In these two cases I got a number, and that tells me where my horizontal asymptote is. What does it mean if I don't get a number over here? But as I said in my last video, you're trying to pattern match when you should be trying to understand, if that's what if your thinking is I see a number and that tells me the asymptote. Remember, this doesn't just tell you the asymptote. What this really tells you is approximately what are the y values when x gets very large? So keep applying that same idea. As x gets very large, what is this thing equal to? So limit x gets very large, limit x approaches infinity of that. So if x is getting bigger and bigger, the denominator gets smaller and smaller, so that should approach 0. So what it tells me is my original function is approximately this, and as when x is big, and when x is big, this is approximately 0. So there really is a horizontal asymptote after all at x equals 0. Did I say x? At y equals 0. If you wanted to fill in the rest of the graph, you just have to think about where is the graph, or where are the y values negative and where are they positive. So I'm noticing that the denominator is always positive. The numerator isn't, though. So what x values would produce negative numbers in the numerator? It seems like whenever x, let's ask when would the numerator be 0. So the numerator equals 0 exactly when x equals -5. So notice there actually is a point on the horizontal asymptote, which is fine. An asymptote isn't like a magical thing that you can't cross, at least a horizontal asymptote isn't, because again, the definition of an asymptote, or like an informal definition, is the y value which your curve is approaching as x approaches infinity or negative infinity. So that doesn't say anything about what's happening for specific finite values of x. All right, so we've got that. So as long as, so this is x equals -5. So as long as x is larger than -5, the numerator is positive, the denominator is positive. So you're going to have some curve like this, where you're still approaching 0, but from positive numbers. When x is smaller than -5, the numerator is negative, the denominator is positive, so overall your y value is negative. So here you're approaching the asymptote from negative y values. So we're at the end now. I'm going to do one more set of examples in a second, but what I wanted you to appreciate was the three original equations looked pretty similar. There was like a number here that was different, there was a sign there that was different. But factoring shows you that the structure is actually quite different. On the surface, they appeared similar, but this one has no holes and no asymptotes because nothing cancels, and there's no values of x that make the denominator 0. So even though it looked similar to these others, the actual like mathematically relevant structure was quite different. In this case, you had something that canceled, and in this case, you didn't. And so in this case, what was a vertical asymptote at -5, in this one, that vertical asymptote became a hole instead because there was a factor in the numerator which canceled it. Okay, so let's think about it from the other side now. You've seen some examples and you know how to think about like what are they doing. So in general, what's the full range of behaviors that are possible when you have a polynomial divided by another polynomial? Well, hopefully it's pretty clear that you could have any number of vertical asymptotes you want, including 0 vertical asymptotes. And if you don't know, think back to the last set of examples. What is it that would produce no vertical asymptotes? So let's construct some examples. See if you can make your own example that has three vertical asymptotes at x equals -1, x equals 5, and x equals 6. So go ahead and produce a function that has 3 vertical asymptotes like that. Pause the video. Okay, here's mine. So the numerator can look like anything you want. The denominator, let's just have x plus 1. Well, I'm going to walk back that statement in a second. Okay, so if these are the factors in my denominator, I know that when I plug in any of these values, it's going to produce a 0 in the denominator, which is going to make a vertical asymptote as long as there's nothing in the numerator which would allow that factor to divide out. So the rule now, so in order to keep these 3 vertical asymptotes, I just have to make sure that none of these are factors in the numerator. So an easy way to do that is just to put a number here. Or, I could put literally anything else. I could have like x to the 7th minus 2x to the 21st minus 5. And I'm relatively certain that this doesn't produce any of those. And that's enough. Let's try and add some more conditions here. What if I wanted to add the condition that there is a horizontal asymptote at x equals, why do I keep doing that? At y equals 0. No, actually, let's not do that. Let's do at y equals 10. Okay, well, so that's easy enough. I know that a horizontal asymptote happens when x gets very large. So what I know is that I need the dominating term here divided by the dominating term there to simplify to be 10. So here the dominating terms are x to the 7th divided by, if I multiply this all out, I'll get x cubed. So clearly x to the 7th divided by x cubed isn't 10. So what I wrote last time works for the vertical asymptotes but doesn't work for the horizontal asymptote. So it seems like if this is going to simplify to be 10, I need the numerator to be the same degree as the denominator. That's got to be x cubed. So that means I can't do... Oh, sorry, the dominating term was actually the 21st power. I missed it. Anyway, it's neither here nor there because we decided that wasn't going to work. So I could have an x cubed here, but if this is going to equal 10, it would really have to be 10x cubed. And then I could have some other stuff here, you know, like 2x minus 17. Again, I want to make sure that I didn't accidentally produce a factor that would divide one of those. But now I've done it. So I have my 3 vertical asymptotes, and I figured out how to make my horizontal asymptote by choosing a dominating term in the numerator that's going to produce a simplified end behavior that's the horizontal asymptote I want. Okay, so what if it was y equals 0? If you were going to just try and plug and chug by matching surface level patterns, it would be like, oh, I have to make this say 0. But that doesn't really, but that just, you know, eliminates this term and it produces a new dominating term here. So that way of thinking doesn't always necessarily make sense. Let's start from the other end. I know that my denominator has a dominating term of x cubed. I want this to simplify to be 0. So what could go in the numerator such that this simplifies to be 0 as x approaches infinity? So let's add a limit in there. So this is going to be approximately equal to something where that same something as x approaches infinity is going to equal 0. Okay, so again, what could go in the numerator so that this approaches 0? And the answer is like literally anything that grows more slowly than x cubed. So the numerator could contain 1, it could contain 100, it could contain 1,000, any constant value. Notice that it could also be like x squared, because x squared divided by x cubed simplifies as 1 over x, and clearly that approaches 0 as x approaches infinity. So as long as you have any lower degree polynomial than x cubed, you're going to get something that simplifies to an expression that approaches 0. So what does that tell us backing up here? That tells us that if we want a horizontal asymptote at y equals 0, we could put any polynomial here as long as it's smaller degree than x cubed. So I'm going to write negative 100,000 x squared plus 8. So let's back up again to what's possible. I hope that this has convinced you that it's possible to have any number of vertical asymptotes, and you can put them wherever you want. After you've done that, it's possible to figure out how to put the horizontal asymptote wherever you want. Let's try and think of a weirdy case. Let's try and think of what programmers call an edge case. So what if I wanted no vertical asymptote, and I also wanted no horizontal asymptote? Well, how could I do that? So if I want no vertical asymptotes, I know that whatever I choose for the denominator has to be prime. It can't have any real valued solutions. It can't factor over the reals. What if we wanted there to be no horizontal asymptote? Well, okay, so let's actually give ourselves a specific example here to work with. So I don't know, I'm going to use let's use our old go-to example. So we know that that one's prime. How do we know it's prime? Because if you imagine the graph, there are no x-intercepts, which means there are no real valued solutions, which means that it couldn't factor, because a factorization would produce solutions. Okay, so given that, what could the numerator look like? Well, let's try out some options. Could it be just a number like this? Think about that. I hope that you said no, because if this is any number at all, I know that the end behavior is going to behave like a number over x squared, and the limit of this as x approaches infinity is 0, which would mean there's a horizontal asymptote at y equals 0. So I know it can't be a number. Could it be a linear equation? Could it be like 2x plus 1? And again, I hope that you see that the answer is no for the same reason, because as x approaches infinity, if I look at the dominating terms simplify as, well, let's just simplify it here. So the x divides the x, so that just gives me 2 over x, and again, that's going to give me a horizontal asymptote at 0. And I hope you can see that's going to happen no matter what the linear equation is on top. Could it be a quadratic equation? Now I'm going to consider the family of all possible quadratic equations. Here, the end behavior would behave like ax squared divided by x squared, which simplifies as a. So if I have a quadratic, that's telling me that it's going to have a horizontal asymptote at a. Its horizontal asymptote is just going to be whatever that coefficient of the leading term is. All right. What about a cubic? So let's do 5x cubed plus some lower degree terms. So this one, the dominating terms would be 5x cubed divided by x squared. Let's take limit as x approaches infinity. So here, this simplifies as, just 5x, right? Because the x squared divides the x cubed. So what does this do as x approaches infinity? As x approaches infinity, this also approaches infinity. So this one doesn't have a horizontal asymptote. This would be a slant asymptote. So it seems like we finally found one that works for our original conditions. The denominator is prime, so there are no vertical asymptotes. The numerator is a larger degree than the denominator, so that means it doesn't have a horizontal asymptote. What if we didn't want it to have a slant asymptote either? I hope you can imagine what you might try. What if we made this like 100? If you imagine the dominating terms now, I've got 5x to the 100 divided by x squared. So that means the end behavior is going to behave like 5x to the 98th power. So in other words, the y values of this function are going to approach the y values of this function. What does this function look like? Looks like that. So that's clearly not a slant asymptote because it's not a line. So what I've been modeling for you here is the thinking process that a mathematician would go through if they wanted to understand a family of functions. We're looking at a family of rational functions. And the kinds of questions you ask if you're a mathematician is what range of phenomena are possible? And you start to get a feel for it by tinkering with examples, and you start to try and notice what about the structure in my examples produces different kinds of behaviors. And then you have conjectures. You think, maybe the factorization of the denominator affects something. Maybe the dominating terms affect something. If you're a mathematician, you would then go on to prove your conjectures. We're not doing that right now. But I think it's a really good skill for you to practice. It's a different mindset. It's not trying to understand the steps of a process that you execute like a computer, because we have computers for that. Instead, you're trying to understand kind of what makes the math do what it does. It's a process of discovery. And that's the thing that's really going to be valuable for you in the future.